normal varieties and normalization, and it is what happens if you try to make a singular variety non-singular in smallest possible dimension, like in dimension 1. So this is a curve, x squared is equal to y third in C2. But then you can obtain that as an image of a map. T goes to t third t square. So this is a singular curve. Obviously singular, you can easily see it. In fact, you can easily check that it is singular by looking at its maximal ideal. So let's call this Z. Z is a graph of this, or a graph of this map, or solutions of these equations. And then, so it's x squared is equal to y, x squared is equal to y third in C2. And then you can take the 0 inside it, the point 0, 0. Let's call it Z. And then you can take m square Z quotient by m third, well, m by m squared, sorry. Okay, so if we think of this as of I mean, all functions are generated by t and t squared, so this is the same as you take polynomials generated by t and t squared and t third. The maximal ideal, M0, is generated by, it has two generators, t third, t second, and t third. This is the maximal ideal. And then if you take the quotient by maximal ideal, the dimension, because this is, the space is the same as t squared, t third, and so on, generated quotient by t4, t5, and so on. So this is two-dimensional. On the other hand, if you have a smooth curve, you can easily see that smooth one-dimensional subspace, subvariety, that the quotient of maximal ideal by maximal ideal square is always one-dimensional. This is because if you have a, because of a theorem of Adamar, you know, Adamar lemma. Which says that on any smooth manifold, if you have M smooth, like a ball, locally, it's a local statement, so it doesn't matter. F smooth or analytic or polynomial functions, on M, f of 0 is equal to 0, and you have coordinates, z1, t1, tn coordinates. Then f is equal to some linear plus f1, where derivative of f1 is equal to 0, and also f1 is sum of t, let's call it g better. So it's g, here I have g. G is t1 g1 plus t2 g2 plus and so on, where g1 gi has a derivative, well, gi of 0 equals 0. This is explicit form of first term of Taylor decomposition. If you have a function which vanishes in 0, it's a linear term plus quadratic term plus second plus third power term and so on. But from this argument, we obtain that if a function if f of 0 is 0, it's in maximal ideal, then f is linear plus square of maximal ideal. Because of this linear term, this term which belongs to a square of maximal ideal. Okay, this means this. Okay, thank you. So this implies that on any smooth manifold, so if you have, so it gives a corollary that if M is smooth, algebraic, just smooth manifold, complex analytic, the argument is always the same. X inside M, you take or mx ideal of all functions such that f of x is 0, then mx by m square x, the dimension of that is the same as dimension of linear functions. This is dimension of m. Okay, and here we have a different situation. It's two-dimensional for this particular singular curve. Then it is non-smooth. But it has a smooth map from it. I mean, just t goes to there. This means that, well, it has a reparametrization which is smooth. And the same happens for all other situations. You can reparameterize singular curves to make them smoother. This is called a normalization. So today I will tell you about normal varieties and how you obtain this normalization in our case. It's obtained as an integral closure. From the algebraic point of view, this is just integral closure of the corresponding grid. Okay, so we start with Zariski topology. This is something we have, I think, discussed. So this is very non-Hausdorff topology. So you have M algebraic affine varieties. Okay, and then closed, Zariski closed. So X inside M is Zariski closed. If X is algebraic. So all closed subvarieties are ones which are determined by algebraic equations. So the good thing about this topology is that it is purely algebraic. If you have some automorphism of your variety, Zariski closed, go to Zariski closed. In fact, if you consider some variety like x given by equations, p1 equals 0, pn equals 0, what you can do, you can consider automorphism, sigma, inside automorphisms of complex numbers over Q. And then you can apply sigma to these equations. This will be another algebraic variety. You just take all coefficients and apply sigma to these coefficients. This would give you another algebraic variety which has the same algebraic property, but it can have different topology. There are examples where the topology of this other variety is entirely different from X, from topology of X, from the usual topology. So this is why people use Zariski topology. Another reason to use it is that suppose you have something like over finite field characteristic P, or then the usual topology doesn't work, and Zariski topology does. So it's this is another reason. Okay, there is a notion of Zariski closure. So if you have subset like L inside M, Zariski closure of L is intersection of all subvarieties containing L. So it's the smallest closed variety, smallest closed subset, which contains X. This is, if you know topology, this is just the same as usual closure, but I mean the definition is doesn't care about Zariski topology. Okay, so let me give you explanation what happens in dimension 1, cofinite. So definition, a cofinite topology on a set, say S, is topology where closed subsets are finite or Z, or the whole S. So if you remember the axiomatic, who remembers axiomatic definition of topology? Not everybody. So axiomatic definition of topology is that M topological space if there exists a class subsets given U if given class of subsets, say O, in the set of all subsets. The set of all subsets is denoted 2 power m subsets of M, which is called open, and a closed the same as complement of open. This is part of the definition. Now axioms. First, M and empty set are closed and open. They're both closed and open. I mean, complement to empty set is M, so it's second union of open is open. And third, intersection of finitely many open is open. So if you go to the complement, this means that the union of finitely many closed is closed, and intersection of any family of closed set is closed. Okay, so we can check now these axioms for the Zariski topology. So the first axiom is obvious. I mean, empty set is just stupid equations, and M is no equations. Now, union of open sets is open. This is the same as intersection of closed is closed. But what is intersection? You just add the equations. So you have some set of equations. Any family of equations, you just to consider union of all these equations, an ideal generated by this union. It would give you intersection of the corresponding varieties. Finally, if you have finitely many varieties, you can take their, this is something we discussed, union of finitely many algebraic varieties is algebraic. You just take products of the equations which define you these algebraic varieties. Am I clear? Okay. Now, and cofinite topology. So what do we need? Closed are finite subset. Any intersection of closed is closed. I mean, it's smaller than finite, so it's finite. Finitely union of finite is finite. Good. And as the first axiom is also true. So the important thing about topology is that you can define continuous maps. People usually define continuous map using epsilon delta, but if you are not last century mathematician, you would define them as maps such that preimage of open is open. This is a good definition of continuous maps, which is much better from, even if you like study first year calculus, it's still better. Okay, good. So I wanted to tell you why this is relevant. So remark, if you have C, I mean, C is algebraic set. Just and you have Z in it. Z is closed, if and only if, is Zariski closed, if and only if Z is finite, or Z is C. Okay, this is what does it mean, Zariski closed? This means that it is defined by a family of polynomials, but every polynomial has finitely many solutions, or everything if it is zero polynomial. This means that you have cofinite topology as Zariski topology for dimension 1, and this then you can see that it's terribly non-Hausdorff. I mean, no open. If you have two open sets which don't intersect, this means that one of them is empty. The only case where you have non-intersecting open sets. Okay. This is the picture of Zariski, and yeah, the important thing that this was the idea of Zariski, and he was interested in maximal ideals. But if you do algebraic geometry properly, you don't work with maximal ideals. The problem is with maximal ideals that they are not functorial. If you have a map from A to B, you have a map from functions on A to functions on B to functions on A. But then the preimage of maximal ideal can be prime ideal. It's not necessarily maximal. It's definitely preimage of prime is prime, but preimage of maximal is non-maximal. So what you do, you don't work with maximal ideals. You work with all prime ideals. So in the gradientic sense, the spectrum of A is all prime ideals, the set of all prime ideals. And then Zariski topology for each x inside, well, x subvarieties are ideals. So you take ideal I inside OX or OA. And then closed subsets are the same as ideals containing I. For instance, if I is 0, then you obtain all ideals because all ideals contain 0. And if I is 1, I mean contains, is not an ideal, then you don't have, here you have prime. You don't have any prime ideals containing 1. So it should be ideals in the sense that 1 is also an ideal. The whole A is also an ideal here. Okay, and then you have, but of course, if you restrict yourself only to maximal ideals, this is the same topology. Now we have dominant morphisms. So f from x to y, this is definition, dominant morphism. If f of x is dense, Zariski dense. Okay, in fact, it's not hard to see that Zariski dense is the same. Well, it's true. It's hard to see, but it's true that in that case you can say you don't need Zariski dense. You can write dense. But maybe I will prove it later, not now. Okay, so the dominant morphism can be characterized. Yeah, important thing. If y has many irreducible components, then this thing should be dense in all of them. Because if it's not dense in one of them, you have a closed subsets, namely complement to this component, which where it is, I mean, anyway, it has to be dense on all components because all components are closed subvarieties, closed subsets in Zariski topology. Okay, now what I wanted to tell you is that morphism is dominant if and only if the corresponding homomorphism of rings is injective. So proposition, if you have f from x to y is dominant if and only if f star from OY to OX, the corresponding homomorphism of rings of regular functions, is injective. It's almost by definition. So if it's not injective, then it vanishes on some function. Proof. F star not injective, then f star of a function a, for instance, is equal to 0. But then, okay, so the function, it gives an ideal, just general, I mean, it's principal, the corresponding principal ideal is denoted ZA here. But then all functions which all functions from all functions on then f star, then f of z belongs to the ZA, or we denote it as VA, the set of zeros of A. This tautology, I mean, there is nothing to prove here, but let's do it properly and try to prove even if there's nothing to prove. So how you prove it? You see that, okay, we have a point. What is point in X is maximal ideal. So Mx is maximal ideal of a point X in X big. Now we're interested in what is its image of this maximal ideal in Y. So f of the corresponding point is the ideal of all functions B in OY such that f star of B evaluated in X is 0, so it belongs to Mx. Okay, but then if f of A, if f star of A is always 0, this means that f star of A belongs to this ideal, to Mx, all right? Because it's 0. And then f of X belongs to the set of zeros of A. Because, I mean, if something vanishes, So if you have is it already clear to everybody or not? So for whom it's already clear and I shouldn't continue? To nobody. Okay, let's do it in more detail. So you have maximal ideals are the same as a homomorphism mx. Maximal ideals are the same as a homomorphism. So maximal ideals in OX, say, homomorphisms to C. This is essentially Hilbert Nullstellensatz. As if you remember, when we proved that the only thing we have to prove, the only non-trivial thing was to see this. Okay, so now you have a homomorphism. How it is denoted here it's not denoted, so let's call it alpha from OX to C. Then you take composition alpha with F, like F star alpha. It's a map from OY to C. And this is image of X in Y, because we know that such homomorphisms are precisely the points. Okay, but then F star multiplied by alpha applied to A is equal 0, because F star of A is equal 0. This implies that F of a point X belongs to 0 set of A. And this is complete tautology in the sense that I didn't tell you anything new. It's just I explained how our equivalence between rings and varieties works. This is how it works. Okay. Let's prove the opposite equivalence. So step 2. If f of x is contained in some algebraic subvariety, it's contained in VA, in vanishing set of, in 0 set of certain function, and then so this function vanishes on the image. A vanishes on f of x, and then f star of A vanishes up, right, is 0 on x. So if this map, its image is not Zariski dense, then so I proved both ways. I started with so if this image is not dense, then it has kernel. If it has no kernel, then it's dense. Questions, comments? It was really nothing. I mean, I didn't. It's really like a sequence of tautologies. You shouldn't be alarmed. Now let's continue the same way. So I'm now interested in the field of fractions. This is something you know from how you obtain rationals from integers, how I obtain rational functions from polynomials. So definition. Suppose you have S inside a ring R. This is ring. And this is a closed subset, closed under multiplication. Then you can have localization. I think we had a very similar definition at some point where we localize just by one element, but you can do localize by all elements. it has several, you write it like S, R of S with the or R of S minus 1, localization ring is obtained by, it should, S shouldn't contain 0. Because if it contains 0, this would be just zeroing. It's not interesting. So it's fractions. The set, the ring generated by symbols. A quotient by S, where S belongs to our set S, and relations. There are two relations. First, A by S plus B by R is equal to AR plus BS quotient by RS. This is for all A, B in our ring, and for all R and S in our localizing set. And the second relation is even easier. It's A quotient multiplied by S quotient by SR is equal to A quotient by R. This is formal. But it's not hard to see that this is how you obtain, this is the formal way you obtain rational numbers, the formal way you obtain fractions, the rational functions, and so on. And today I would be interested only in S is all non-zero elements. So if you're lucky and your algebraic variety has no, its regular functions have no zero divisors, which is equivalent to irreducibility, then you have proper fraction field, so definition. Let Z be affine irreducible variety. If you remember, irreducibility is precisely where irreducible is the same as the ring of functions has no zero divisors. It's a domain, I think it's also called. This is something we had. Should I remind you why it is so? Okay, good. But it was, I think, lecture 3 or 4 or something, quite long ago. But anyway, the field of fractions of rational functions on Z is the same as localization of OZ in all A which are non-zero. And generally, you can define field of fractions if A ring with non-zero, with no zero divisors, then K of A, field of fractions, of A is obtained by as is a localization of A in all A which are non-zero. So you have field of rational functions, which is just field of fractions of the ring of regular functions. Am I clear? You should ask questions as much as possible. It helps, simplifies my work. So please ask questions. We shall go far faster, in fact, if you don't. Okay. Now, there is this notion of birational map. This is an important notion. Birational map is a map which induces equivalence on the ring field of fractions. But before that, I should define you what happens with the field of fractions, with the field of rational functions. If you have a morphism, nothing good happens unless you have a dominant morphism. But if you don't have a dominant morphism, everything is okay. So lemma, suppose you have f from x to y, dominant, then f star defines a homomorphism from k of y to k of x of fields of rational functions. There's nothing to prove. I mean, you have a fraction like a quotient by b, a fraction in k of y, where f and a and b are functions on y. Good? Then you take f star of a quotient by b is equal to f star of a quotient by f star of b. This is non-zero, so this makes sense. And then you check that these relations are satisfied. There's nothing to check. Make clear? Good. What do we need? Anything else? Yeah. Also, what I wanted to say that this is important, and I forgot that dominant x irreducible, then y is irreducible. Let me explain that. So the idea is that the preimage of Zariski closed is Zariski closed. So any morphism, so if you have f morphism of affine varieties, then f star of Zariski closed is Zariski closed. I mean, preimage of algebraic is algebraic because you just take the preimage of the corresponding functions, and we define this algebraic subset. So this means, actually, this is precisely the definition of continuity. So this means that what I told you just means that in Zariski topology, any algebraic map is continuous. And then if you have y is union of ui, yi, then f star of x, of y, is union of u, y, I. Oh, sorry, f star of yi. Okay, so what could possibly happen is that one of these components, so you take their preimages, f preimage, sorry, you take the preimages, and they are not irreducible components of x, or not a union of irreducible components. So what could in theory happen that this is not a irreducible decomposition, but it can't happen because f of x intersected with yi is Zariski dense. This is because, I mean, this is dominant map. The image is Zariski dense. So the image in any component is Zariski dense as well. And then this gives you a non-trivial, this implies that the preimage is a non-trivial union. So if you take this is really, this set's really different. Okay. I think here we have some different argument. So let me give you this different argument. So yeah, I didn't. The problem is that I didn't define you divisors. Divisor is zero set of a function. Okay, so if this is another proof of, sorry. Yeah, so we have an embedding, or if this is dominant, we have an embedding, or y embedded to OX, right? I mean, this is something we already discussed. And then, if you have if X has no zero divisors, then Y also cannot have zero divisors. This is much simpler than what I told you here, but slightly less geometrical. Questions, comments? So in fact, this, you can forget this. This is a nice geometrical picture, but this is much easier. Okay. Now let's discuss divisors. I told you that divisor is a variety which is defined as zero of a function. This is not entirely true. The problem is that in some special situations, what you can have is you have a function f belongs to OX. You take a zero set of f, and then you find that it is a union of two subvarieties. But none of these subvarieties, like it's irreducible, it has two irreducible components, z1 and z2, or many of them, like lots of irreducible components, irreducible components. But these components are not zero set of any function. This happens. It doesn't happen on C, it doesn't happen on Cn. It happens sometimes, but it's sort of hard to find examples where it happens, but it does. So I will define principal divisor. Principal divisor is zero set of a function, and divisor is, and it's better to have a irreducible variety, otherwise. Or you can say that, okay, you have a function which doesn't vanish on irreducible components. So you have a function not vanishing on irreducible components of X. So it's a function f which belongs to OX. It doesn't vanish on irreducible component. And divisor is a irreducible component of principal divisor. There are reasons why the notion of divisor is good and notion of principal divisor is bad. The main reason is that divisors, you can define them locally in Zariski topology, and principal divisors are global notion. But we shall not go there now. What is divisor? It's just codimension one subvariety, that's all. So like you have C2, you have a function, its zeros are curve. Okay, so what do we want? First, the complement to a divisor, to a principal divisor at least, or just any divisor, in fact, is So here it is about principal divisors. But, on C every divisor is principal. Anyway, so remark. Suppose you have X inside Cn, algebraic, affine subvarieties, subvariety. And then you have D inside X, principal divisor. Divisor given by F, which is a function. Then X without D is also affine. Well, it's affine in other coordinates, not in that coordinates. This is because, and given in C, so this was Cn plus 1, given by, you have an ideal, so it's given affine variety, Ix, its ideal. Ideal of polynomials vanishing in X, given by Ix, and then you add just one element, Ft plus or minus 1 is equal 0. So you take this is the ideal you take. This is something we have already done. So you want to invert F. You just add another variable, and you write Ft is equal 1. So the projection from this, the forgetful map, is clearly injective because T is just F minus 1. It doesn't give you any new information, but then now it's invertible. So if you have I, like Mx, maximal ideal in this xd, defined by this. This is the common zeros of this ideal. If you have maximal ideal in this variety, xd, you can take its intersection and mx intersected with ox. And this will give you a maximal ideal, but then f cannot vanish on mx, because then 1 would belong to x. So if you have maximal ideal which contains this ideal, its intersection with x doesn't belong to zero set of f. But if it doesn't belong to zero set of f, you can just lift it to to Cn plus 1 and take a maximal ideal which contains it. So this one-to-one equivalence. Okay. So this is sort of standard. We have already done this when we proved the Hilbert-Nullstellensatz. Yeah, so now I wanted to give you this as an example of birational map. So what is birational map? Definition. F from x to y, dominant. Morphism is called so let's suppose that x and y are irreducible, called birational map. If the corresponding map k of y to k of x is an isomorphism. Okay, so birational maps are maps which induce the same fractional field, and this is an example. So xd is obtained from x by adding to the corresponding ring just one variable, just localizing with f. So the field of function doesn't change. Okay, and there's an important observation. Do you have any questions, comments? Should I go? Yes, please. Because the ring O of xd is obtained from O of x by localizing with f. We just added f, but we added also equation that ft is equal to 1. This is the same as localizing formally. And then, of course, localization of the whole thing is the same, because when you localize, I mean, when you take field of fractions of OX, you just localize all elements of OX, non-zero. So it's one of them is the same as another. More questions? Okay. So important thing about birational morphisms is that they're all equivalents outside of a divisor. So theorem. Suppose you have f from x to y, morphism. In fact, it's one and only one, but let's start with birational because the opposite side is clear. So birational morphism. Then there exists divisor d inside y such that the corresponding morphism from x without f minus y minus 1 of d to y without d is an isomorphism. So birational maps, they're equivalences outside of a divisor. Okay. Even principal divisor doesn't matter. I mean, you can always add more components to your divisor if you like. The statement will still do. The converse is clear. I mean, if you have an equivalence without a divisor, then you notice that if you remove a divisor, the field of fractions doesn't change. So if it was, after removing a divisor, it was isomorphism, then it was isomorphism on functions. So the converse is clear. Okay, so let's prove it. Proof. Step 1. So all our rings are finally generated. This is by Hilbert, well, by definition, essentially. So OX is finally generated. Then there exists F inside OY. And what I want to tell you is that you can invert this map, but so I would just explain the geometrically picture. So you have x to y. This gives you OY to OX. You want to invert this map. You can invert it if you add fields of fractions. So I'm going to invert it, but then for each, you have generators here, like how it was they were denoted. Yeah, so for all generators here, you can, for all A inside there, you can map A to some to some fraction, b over r, right? Because on fractions it's an equivalence. But then you take all generators, you take all denominators of these fractions, and you multiply them. This gives you this f. Okay. So there exists such f, such that for all a inside OX, there exists b inside OY, such that b is equal to f of a quotient by f power n. Okay, so how you obtain this? You take a generator here. You obtain it is an image of some fraction in, so for each generator xi of OX, right? There exists a fraction bi quotient by f I, such that this is f star. Xi is f star of bi quotient by fi. Okay, now we multiply all fi. F is a product of all fi. And then for each product, like you take several xi, you take their like some polynomial, like homogeneous polynomial of fi, for instance, or non-homogeneous, doesn't matter. It will also be an image of something which has denominator, which is just product of several fi's. That's all. And then you can write f power n. Okay, so this f, its zeros will be our divisor. This is the second step. Step 2. Am I clear? You should ask more questions, unless I am very slow, and then you should somehow let me know that I'm slow. Okay, so we take z inside y is set of all zeros of f of f. Then O y without z, this is something we discussed, is the same as OY localized in f minus, localized in f. Then we already know that since this is a dominant map, OX goes to OY, oops, sorry, converse, OY goes to OX, is an embedding. Embedding. So the same is true of OY of f minus 1 goes to OX of f minus 1 is also embedding. This is two injective maps, two injective homomorphisms of rings, but then this is also surjective, as we just proved in step 1. Okay, now let's look what is this thing, and this is of course the ring of functions on, now we take OX without f minus 1 of z. Because what is these points? This is precisely the points which arrive to z. So to obtain, so the corresponding divisor is just zeros of the preimage of f. Okay, questions? Comments? Anything clear? Okay. Let's have a break, like 5 minutes until, and if you have questions, you can ask, and then I will slowly go to integral dependence, but really slow, because I have a feeling that you are overwhelmed. Until 22:03. The idea is that you have a map which is birational, it's finite. So if you have things like this, x squared is equal y third, you have normalization, which is a smooth map from smooth manifold, which is just spectrum of C of t, which is finite and birational. And normal variety is one which doesn't admit this. So this is the idea. For each variety, you have a special variety which is called its normalization. And this is useful because you can apply that to many things, essentially by using this formalism of finite maps. But so we are going to discuss finite maps a lot. Okay, so the first definition, this is just something we have already done a bit. You have A inside B rings. You have B in B element. And then you take subring generated, A of B generated by B. This is a subring generated by A and B. And B is called integral over A, or integrally dependent, or something like that, if A of B is finitely generated as a model. The finitely generated as a model is completely different from finitely generated as a ring. I mean, there's nothing to do between this. Is both finitely generated, but they're different. But we already had that. Now, we also had this notion of monic polynomial. So definition. P of t inside R of t, called monic polynomial. If the leading term coefficient is 1. This means that P of t is t power n plus a1 t power n minus 1 plus and so on plus an, just n, plus t a n minus 1 plus an, where ai belong to your ring. Yeah, and the following claim is sort of trivial for non-Noetherian rings, for Noetherian rings, and it's, in fact, most of what I'm telling you in that part works for non-Noetherian rings, but it's sort of silly, and let's do with Noetherian. But this claim you can prove for any. So claim. Suppose you have B. So you have A inside B as before, and A Noetherian. Well, not necessary. B, then B inside B, integral over A if and only if the chain of submodels terminates. Chain, you have A, which contains an A plus BA, which is contained in A plus BA plus B square A, and so on, terminates. And this is actually equivalent to B being a root of this equivalent to there exists a monic P of T in polynomial in A such that P of B is equal to 0. So B is a root of monic polynomial. These are three equivalent statements. Oops, sorry. So proof. Well, if the chain terminates, this means that B power n is the sum of B I, AI, where from I goes from 0 to n minus 1, right? This is equivalent. So this, the first, the second, and the third are clearly equivalent. Oh, right. Integral is precisely monic polynomial. I shouldn't write that. Sorry. Yeah, but no, it's okay, because sorry, I'm just forgetting what kind of definition I put there. So B is the root of monic polynomial. Okay, now finally, if this model, this is clear. If A of B finitely generated, then we take generators like x1 dot xn generators, and suppose they're all polynomials on B, right? Polynomial dependent on B, and suppose that n is bigger than all degrees in these polynomials. You take B power n is equal to some AI xi, but this is the same as sum of AI Ci B power Ki, where all Ki are less than n. So finally generatedness implies the monic dependence. Okay, and converse, if you have this dependence, then then everything is clearly finally generated. There's nothing to prove. Anyway, it's probably easier just to look at this a chain and realize that finely generatedness is for Noetherian rings is precise determination. So then there's nothing to prove. But this statement is sort of still takes Noetherianity. So remark, if A and, well, X and Y inside B, which contains A, are integral, then X plus Y and XY are integral over A. And I assume that A is Noetherian. I'm not sure you really need Noetherian for that, but so how you prove that? Okay, you start with the proof is precisely the same as we proved that the sum of algebraic is algebraic. So proof, you take A of X. This is a finite A model. A of X of Y is finite A of X model. Good. Then there is finite set of generators which are expressed through A, X, and Y. Then A of X and Y, finite generated A model. I repeat, you have this is finite over that. This is finite over this. Then you have generators of this ring, like finitely many, which generated it as a model. And then this ring has finitely many generators which generated over this model. You just multiply them all. And this gives you generators of this as a model. Something we already had. And now Ax plus Y and Xy are they belong to a submodel. And a submodel of finitely generated because A is Noetherian. Okay. And this is probably the last for today. No, not the last. We still have some time. So integral closure is something you always do in number theory. This is important in number theory. So, and all examples of that is, of course, number theoretic. Well, most examples. The typical example of integral closure is, well, let me define it first. Definition. So suppose you have a ring, no z divisors. Then integral closure of A is a set of all integral over A elements in the ring of functions in K of A. Well, let me give you an example when it is integrally closed is one which coincides with the integral closure. Yeah, so in fact, you can take integral closure inside something. So if A inside B, integral closure of A in B is set of all integral over A elements in A in B. So this is integral closure as well. Okay, now a definition. A is integrally closed. If its integral closure in K of A is A. So this means that if you have a monic polynomial which has roots in the field of fractions, these roots are actually belong to A. And this is algebraic notion. It has a geometric counterpart. So definition, X, suppose it's irreducible variety called normal if OX is integrally closed. Okay. And if X is not irreducible, it is normal, X is normal, if all its irreducible components are normal and adjoint, don't intersect. And the idea, the main utility of the whole business is that every space has its own canonical normalization, which depends on its factorial and. Okay, so we have another geometric equivalent remark. X is normal if and only if each birational map, suppose it's irreducible, affine. It's if each birational map y to x, which is finite, is an isomorphism. So to see that, you just notice that what does it mean that is birational? This means that OY belongs, it's a subset of K of X, but because it's mapped to here, OX is mapped to here, so OX contains this. And they have the same field of fractions. Now, finiteness means that it is integrally closed. So what is finite? Finite means that all elements generate finitely generated models. So this is just another wording of the same definition. Okay, so what is important, and now I will stop and continue next time, that if a ring R is factorial, then R is integrally closed. Converse is false. So even in number theory, you can have things like z of square root minus, I don't know, 5. I think already if you do with 5, this won't be factorial, but it is integrally closed, I think. Oh, let's write some very big prime number that's most like probability almost 0 that it is factorial. I think there are maybe finitely many factorial primes for this. This is factorial. And for big primes, they are definitely integrally closed. It's an easy exercise for you. But in fact, when you do algebraic geometry, you work with smooth varieties. And it turns out that if you have a smooth variety, you can remove lots of divisors. You obtain a local ring in the end. And for them, for them both things are true, and this is how you obtain integrally closed. So it's really important. This is the basic thing about integrally closed, is that somehow you reduce everything to factorial. Okay, but then I will start with this next time. Thank you very much. If you have questions, feel free to ask, of course.